Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about DART mission. So let's dive right into it. So what exactly was the aim of this DART mission? Well, launch a striker with self-guidance system, because you have to understand when you are talking about planets, they are kind of known things, meaning they're big, they are known, you can go to it. When you're talking about asteroid, you could be talking about something that is very new, like as in like we have just detected it like few months ago, and the orbital data and trajectory and all that could be very sloppy. So we have to rely on self-guidance system, and not to mention these things are very small. So fundamentally the tracking system have to be on board. We cannot just like, okay, go there. It has to be like, go there, use your own senses and calibrate yourself in order to like how to fine tune, finally aim it. And then you have to understand, this is the first time a planet in entirety of solar system is fighting back, meaning we are basically taking vengeance for dinosaurs, so to say. And why can't we just defend quote unquote planet Earth from any sort of this impact? Now again, we were very lucky, this did not made landfall. If it had made landfall, like this is real world, we would not be talking about Hiroshima and Nagasaki. Those will look like a children throwing temper tantrum. That's how bad this thing could have been if it would have made a landfall. Like serious. Like we are talking about some serious thing here. Now here's the deal: we cannot deal with this flat out. Like on paper, we can launch things and do things. It will have, we have no idea what effect it will have, simply because we do not know how things react in deep space when they are dealing with low surface gravity, and we are dealing with various composition, and we have no idea what will happen if we actually manage to hit it. Because here's the deal: you give gravity's equation to multiple scientists. It's like, here's the gravity, here's the best understanding of gravity we have, model a situation. Everybody is coming up with different answer, meaning some scenarios like if it's a loosely bound, you will just fire anything to it, it will just penetrate through, because it will be traveling at orbital velocity. Speed is so high, it's just like a sniper bullet. Done. Nothing happens. Like it does not impart enough energy into the material to change anything. Basically, it's useless. Another could be, you can hit it, but it will blow off enough chunk of the material on the other side without transferring energy to it. So meaning the mean or mass will still remain the same. It will not change the velocity, direction or anything like that. So you get that, like same mathematics, same equation, and both of them are valid solution. So we have no idea what will actually happen if we do it. So we have to do it. And you have to understand, whenever we do computer modeling, there is a feedback loop. For example, you design an aircraft system. You use best computer knowledge, best computer defined systems that you can do, and you create a model. That model has to go to wind tunnel. Then the feedback data from that wind tunnel goes into computer to refine the parameters. That's how you create a feedback loop, and that's how you get amazing results. If you do not have that feedback loop, you're just lol. And that's the reason why I still have wind tunnels even with F1, even with ludicrously powerful computer fluid simulation models. We have to do that. Without that feedback loop, it's just not good enough. So we have to do it in order to know, can we actually stop this from happening? So that's the aim, basically take vengeance for our brothers, fallen brothers. So what's the use behind it? Well, asteroid impacts are inevitable. Like, let that sink in. Like, this is one of those things that is very hard to understand. So I give you a best example for that. The moment a child is born, the only guarantee that child has in this universe is that it's gonna die. Now the question is when. So same thing happens here. It's not a question of if this is gonna happen, question is when this is gonna happen. So it's the same example, like child could just die like 10 years from now, 20 years from now, 50 years from now, 80 years from now, 90 years from now, 130 years from now. So all those things will have a completely different result. So that's the whole point. We have time, we have to utilize it well, because we do not know, our name could be on the chopping block, we would not know it. And here's the one, big enough is more than enough. One is enough. It's like, oh, we will have second chance. No, sir. No. Like what happened to dinosaurs? They were like little boy. There are big boys, and these big boys, if they come to make love with Earth, bye-bye crust, meaning Earth's crust will be removed. There won't be any life form left. It won't create a crater. It won't create an ecological crater. It will remove what we call Earth itself. So fundamentally, one bad one, bye-bye Earth. Permanently. There is no backup. There is nothing. So it is real, it is serious, and we have observed this sort of thing, this sort of big boy events in Jupiter, and we know for like it affected Jupiter. Let that sink in. So we know for a fact these things are happening, these are real, the same way like death is real. So we have to create a plan for it, because we do not know how to deal with it. We're like, okay, we can launch a rocket. Here's the deal. In movie, we can just have a thing that can go to a thing, then we can land a thing, then we're gonna drill a thing, then put a nuke there. We don't know whether it's gonna do anything or not. So we have to do it in real world. And here's the deal. Targeting in real world is far more difficult without guidance, because again, you cannot rely on Earth-based system. Sometimes they will be very small, sometimes they will be very far, or worst, both of them, very small, very far, will not know how to target it. to give you a context of that, how difficult the targeting is, when the DART mission actually went there, all it was seeing is the main system. It was not seeing the moon that it's supposed to track it. It literally was tracking system in such a way that it's like, okay, 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 okay. When it became close enough, then it started to notice that there is a small thing. Then the computer was like, okay, that's the small one, let's go to that. It had to do course correction. Like almost when it's reaching to it, there's like, oh, now the course correction. So that's why we have to figure out real targeting system. Now be mindful, people are saying there was like aircrafts engineers know how to deal with it. Missile engineers like, bro, this is what we do on Tuesdays. It's very easy. Again, you have to do some cross-pollination from missile engineers to NASA engineers, but this should be doable for humans. Like it's like, bro, we got this, we got this. We can detect something. And if you are talking about something that is like, compared to a black background, one thing, you're like, wait, bro, we're gonna hit you. Even at orbital velocity, we're gonna hit you. So again, some people are saying, dude, it's just like military flexing. It's like, bro, we got this. So let's see. And what effect an impactor will actually have. It's like we have a stuff, it's heavy stuff, we hit it, what happens? We don't know. It's like, does the chunk blows out on the other end? Does it transfer enough delta V? Does it change the velocity? We have no idea. We have to do it. What we are trying to find out is energy transfer efficiency from impactor to asteroid. That's it. That's the core variable that we are trying to figure out. What's the coupling efficiency basically? We pump it, what happens? Does it slow down? Does it change direction? Does it like just blow off materials and just like no big change happens? What happens? We have to do it. So change in delta V direction, that's all things that we are figuring. That's why recently there have been so much, attempts to getting closer to asteroids. Navigation systems are improving drastically. So that's the use of it. Ironically, this is a really useful tool. Then let's talk about the impact that happened recently. The guidance system, the job very well, bullseye. Now again, that's why it's not a big deal, because people who are dealing with missile system, they're like, bro, this is like just basic thing for us. And again, I'm showing a very close-up of GIF this, but when you watch the full video, you're like, it's not visible. Like that's how small it is compared to the main one. So it focused on the main one, it get close enough, then it can see the small one, and then it retargeted. So that's why I said like targeting system is surprisingly complex. It happened on 26 December 2314 Universal Time Coordinate, and this velocity was 6 km per second or 21,600 km per hour. That was fast. Orbital velocity kind of fast. Now, what was the energy? Energy was like 3 tons of TNT, meaning it would have been equivalent if you put a basically 3-ton TNT boom device there. That's how much energy. Now, what kind of change we are expecting? We are expecting from 1.75 centimeter square to 2.54 centimeter square. And like think of it this way, like this happened, like this is real world observatory data, is that something happened and then like say, poof, whole chunk is blown out from this side. Now we do not know whether those chunk stealed majority of the energy or a majority of the energy was deposited. That's why we are doing this test. Without it, we'll have no idea. Like nobody even knew like this sort of like weird structures can be formed when you are actually impacting it. And more detail we'll get with time. So we did the impact. The part 1 is sorted. So how we are observing it? Well, primary observation, you have to understand this. We are using everything. Every tool that humanity has at this point in time, every tool that can look at it is looking at it. For example, Hubble Space Telescope. Like think of it this way, like nobody figured out like why the heck it became bright for 8 hours. Like it literally started to glow. Why? Like is it reflecting so much dust, or the dust is like not blown off, is not settling around on it? Like we do not know. We do not know what exactly is causing this. That's why we are studying it. James Webb Telescope, now be mindful that is infrared spectrum, so energy signature is different, so we have to collapse both of them, then create a much better picture. So both of the telescopes are working, and then we have main boy, that is like 6U CubeSat basically, that is Leica from Italian, and it's supposed to do close-up study. Now be mindful, this is a tiny object and with a tiny solar panel, with a tiny camera. So inherently do not expect GG image out of it, and not to mention because of the antenna strength, it is inherently sending almost like thumbnail. So I was confused, like when I saw the images that are coming out of it, it's like all NASA is saying that it started its mission after the crash, meaning it has captured all the image, it will slowly transfer all the data to NASA, basically Deep Space Network, but it will take time. So it may have already taken amazing photos, it's just like we have to wait, slowly download the data, offload the data code, but it could take time. And almost all ground-based telescope that can look at it is looking at it. So let that sink in. Everything, every Tom, Dick and Harry can look at it, looking at it. And this puppy will give us the final, close-up detail. So we have to wait now. Now, why we have to wait when you have so much data, we have looking at so much data? Well, reality is that we are trying to collect as much data from as many instruments as possible. Like we don't want like this is first time in humanity we have high grade telescopes, multiple of them in orbit. So we are collecting all of them. Multiple high-grade observatory on Earth, we are using all of them. So it's going to take a lot of time. So what we are actually trying to observe, like, okay, we launched it and I specified basically this puppy, Dimorphos, is tiny boy. Like basically the dart actually get close to enough where it was looking at Dimos, but it could only look at it. And it was like slowly trying to get close. Then it became very close. Then it started to notice Dimos. Then the targeting focused on this. Now Leica cam was ejected out of it before the collision. So this will slowly go to near impact site. Hopefully it will give greater photographs. Now again, that will take time. Even if it's already happened in real world, it would have already happened. The data transfer will take very long time. Again, tiny object, tiny is basically tiny power budget, very slow data rate. So what we are trying to observe is basically minute changes in brightness. That's what we are trying to observe, because these things are very far, very small, inherently not big enough where we can just look at it, quote unquote, we can't look at it. So why this object was chosen for a very clever reason, because it has orbit around a lightweight object. We can change the orbit even with little bit data weight, and change in orbit would be measurable simply because Dimorphos goes through eclipses, meaning Earth, Dimorphos, and this Dimorphos goes around it, around it. So this moon blocks it. So blocking on that, like you can observe it and you will notice a dip. Basically the brightness will go down. You can observe it. Benefit, you can clock it, as in like the brightness went down, took 12 hours later, brightness went down again, another 12 hours brightness. That means gives you the orbit calculations. Now we have the orbit calculation. Now here's it. We have changed it. Now how much we have changed it? That will show up in the clock, and it will slowly accumulate. That's why we have to take some serious patience medication here, because it will not happen like, oh, we just knocked it, it will change automatically. No, it will slowly settle into its new position. So we could literally have 11 hour 59 minutes. Next time we'll have 11 hour 58 minutes, 11 hour 57 minutes. It may settle down to like 11 hour 40 minutes, let's just say. So, but it will take time, multiple orbits, and we have to do multiple of these calculations from multiple observatory to verify and quantify it. It's like, yes, exactly this much change has happened. So it will take time. That's what we are trying. Eclipse periodicity, it will take time. So, and we need multiple observation for accuracy's sake. So before we know the full impact efficiency, meaning we had this much energy, we know how fast that puppy was traveling, we know how much energy it inherently dumped onto it, we got that, like 3 tons of TNT, we got that, awesome, no problem. But here's it, how much oomph it was transferred, like, and how quickly, like, does it take very quickly to settle? Now we're going to refine our mathematical model, because here's the scientists specified it very well, is that we think we know the mass of Dimos. That's the reality of it. We think we know, and we are within good margins of it. But here's the, that's all we have, good margins. The margins could be like, 500 tons to 600 tons. Now here's the deal. If something is coming towards us, you cannot say, we think like 5-10% off. Nah, you have to be precise. And especially that's why we have to knock things to actually figure out is like what kind of velocity transfer, what kind of coupling efficiency we have. So patience is key. And this is the first time humanity is fighting back. This is kind of amazing simply because we as a human civilization is like, okay, we understand we have to have Earth insurance policy and we are actually investing in it. That's amazing to see. So again, it will take time, and this is Mark 1, and I'm expecting Mark 2, Mark 3, Mark 4, because at the end of the day, we should have like a rocket a day. Again, we are already at that point. So we'll have, NASA should have the ability to just like commandeer any rocket. They're like, bro, we need emergency Earth first. Take this rocket, put this payload, launch it. Then we're gonna, by that time, we'll collect more information, build a dedicated, striker for it, and then launch it. So we should get to, situation handling very quickly. Again, that's far away, but that's what we are aiming for. Having a whole toolkit that's like, we got this. We got this. Right now, this is the first tool. So this was my presentation on DART mission. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.